Today's lecture is on successive approximation analog to digital converter. This analog to digital converter consists on an operation amplifier which acts as a comparator, where at non-inverting terminal we have input voltage and at the inverting terminal is fed with the output of a digital to analog converter DAC, which of course will have a reference voltage, and input to this digital to analog converter is a successive approximation register, and the output of comparator is again fed to the successive approximation register. When comparator output is high, and that is logic 1, then it will increase its output. So how does it start working is, first it will set the most significant bit B2 in this case to 1, whereas D1 and D2 bit to 0. Now for this input, if the comparator input is 1, and then it will set D2 to 1, and next it will try for the other bit D1 and D0, and if comparator output is coming out to be 0, then it will set that bit to be 0 and try for the next bit. So first it will make start with the most significant bit 100. Corresponding analog signal it will generate digital to analog converter, and it will compare it with the V input. If it is high, V input is high, then it is still high, then it will generate comparator 1, so it will change the bit to next significant bit to 1. If the V input is lower, the comparator output will be 0, so it will change that bit that it has just made 1 to 0 and try for the next bit. So let's say most significant bit it made D2 to 1, and then it will compare whether the digital to analog comparator output is V input is actually greater than the digital to analog converter output. If yes, then it will set D2 to 1. If no, it will set D2 to 0. So now again it will try whether it D2 was 1 or 0, then it will again check. It will make next bit 1 and again check whether it is this magnitude is greater or lower. If it is not greater, then it will set it to 0, and otherwise it will set it to 1. So in this way we will get a different combinations. So we will get a digital output correspondingly 0 0 0 0 0 1 0 1 0 0 1 1 and 1 0 0 1 0 1 1 1 0 and 1 1 1. Now let's see an example. For let's say V input is V in is to 5.2 volts. Okay, so first it will compare. So of course, if the V input is greater than V100, V100 means D2 is 1, D1 and D2 are 0. So correspondingly, let's say digital output will be 4 volt. 2 to the power 2 to the power 1 2 to the power 0, it will come out to be 4 volt. So if the 5.2 volt is greater than 4 volt, that is V100, the answer is yes. So it will go downside. So D2 is set at 1. Now it will make next most significant bit to 1. So it will be V110. So correspondingly digital output, analog output will be 2 to the power 2 plus 2 to the power 1 plus 2 0. So 4 plus 2 equal to 6 volt. So if 5.2 volt is greater than 6 volt, the answer is no. So it will go up. So it means the d1 is now set at 0. Now it will try 1 0 1. So correspondingly the code, the output voltage, let's say that it will generate will be 4 plus 0 plus 1, so that is 5. Now it will try, okay, is the 5.2 is greater than 5? The answer is yes, so it will go towards yes. So the digital code that we are getting will be 1 0 1.